Section 14.3, we're looking at change of variables and polar coordinates. Our objectives are to write and evaluate double integrals in polar coordinates. Here's an example. You want to set up and evaluate a double integral to find the area of this region in quadrant 1 that's bounded by x squared plus y squared equals 4. Now you can draw vertical rectangles or horizontal rectangles because this is vertically and horizontally simple. If you're drawing vertical rectangles, you would have a bottom y equals 0 to the top y. You would solve this equation for y to get y equals the square root of 4 minus x squared. And then your bounds for x would be from 0 to 2, and you can evaluate a double integral that would give you that area. However, we are going to be looking at polar coordinates, so it is possible that we can simplify this problem. The polar coordinates r comma theta of a point are related to the rectangular coordinates x, y, and these are the conversion equations we've used in the past, where x is equal to r cosine theta and y is equal to r sine theta. We know that r squared equals x squared plus y squared, and tangent theta is equal to y over x. So let's look at these regions and use polar coordinates to describe each of these regions. For the first region, you have just this quarter of a circle in the first quadrant. And when you think of the radius and the angle that go into this region, you can think of a smallest radius starting from the origin out to the largest radius, in this case is 2. So from the origin out, the radius is 2. Now the angles, when you measure angles in polar coordinates, the positive x-axis has an angle of 0, and then as you rotate counterclockwise to the y-axis, that angle would be from an angle of 0 all the way up to an angle of pi over 2. So that's how we can use polar coordinates to describe this region here, where the radius is from 0 to 2 and the angle is from 0 to pi over 2. For this region in part B here, we can look at the radius going out from the origin, where the closest radius here is a radius of 1, and then going out further, the radius is 3. So the shaded region is between the radius of 1 to the radius of 3. The shading is in between a radius of 1 and 3. Now the angle, if we start measuring at the positive x-axis, is here at 0 and rotating the entire way around to 2 pi. So your radius is from 1 to 3, and the angle theta is from 0 to 2 pi. All right, so this is a way we can use intervals to describe that region. Again, in that first region, that quarter of the circle, the radius was from 0 to 2, and the angle was from 0 to pi over 2. In part B, the shaded part was in between the circles, where the inside circle had a radius of 1 and the outside circle had a radius of 3. So we can say that r is between 1 and 3 and the angle is between 0 and 2 pi. Now double integrals in polar form is going to require us finding a way to find area of circular sectors. To define a double integral where we have z as a function of x and y in polar coordinates, you're going to consider the region that's bounded by the graph where the r is equal to g1 and r is equal to g2. So we've got this region that's bounded by this graph r of g1 and r of g2, and by the angles theta is equal to alpha to theta is equal to beta. So we've got this region here. Notice it's not vertically simple or horizontally simple, but in this case we can say it's r simple because our inside radius is this g1 function and our outside radius is this g2 function, and our angle goes from a small angle alpha to a larger angle beta. Now, instead of partitioning these into vertical rectangles or horizontal rectangles, what we do is we partition them into small polar sectors. So it's like you're going to be slicing it through the origin, slicing it like a pie, and then also slicing it using concentric circles. Then this little representative sector of a circular ring is what we're going to be finding our differential area for. Now, that little sector here of a circular ring, we could find the area of that. The way you find the area of a sector of a circular ring is to take the average radius, you have an inside radius and an outside radius, and then you're going to multiply it by the width. Now, the width in this case is going to be, it's the angle times the average radius times the width. So we get this conversion equation for differential area. Our radius, we go from the center to the circular ring. The differential r, that's your little change in the radius. And then your differential theta, that's your change in the angle. So differential area for this chapter is going to be r times dr d theta, or it's going to be r times d theta times dr. So when we substituted the differential area in the previous section, we found that dA was either dy dx or dx dy. Now in polar, it's going to be r dr d theta or r d theta times dr. So this is theorem looking at change of variables to polar form. We suppose we're given a region, and the radius is in between these two functions of theta, and the angle is between these two values, alpha and beta. And we could say that there's a double integral r of a function of x and y dA can be converted into polar form, where this x is going to be replaced with r cosine theta, y is going to be replaced with r sine theta, and dA is going to be replaced with r dr d theta. So your inside bounds are for your bounds for your radius, and your outside bounds are your bounds for your angle theta. So in this example here, to set up and evaluate a double integral to find the area, we are slicing this, instead of a vertical or horizontal rectangle, we're going to be slicing it like a pie. And our bounds for the radius is going to go from 0 all the way to 2. And our bounds for the angle, and our bounds for the radius would be from 0 to 2. And the bounds for the angle theta would go from 0 to pi over 2. Okay, before we get into doing that, let's look at the different types of regions that we can find using these polar coordinates. We can have R simple regions, and that way, in that case, if you slice it, if you slice the region like a pie, then the inside radius is defined by a g1 function, and the outside radius is defined by a g2 function, where your smallest alpha to your largest angle beta. We call this R simple. If you can slice it like a pie and the inside and outside radius functions are constant or the same, then we call that R simple. And if it's R simple, the order of the differential area will equal R times dr times d theta. Now if it's a theta simple region, like we have shown here, you slice it using concentric circles, and the smallest angle to the largest angle are defined by functions. Okay, in this example, we're going to be evaluating a double polar integral. You're going to let R be the region lying between the two circles, and we want to evaluate this double integral. So when you are evaluating integrals, it is important to sketch the region. And in this case, the region is between the circles x squared plus y squared equals 1 and x squared plus y squared equals 5. We've got two circles. The first radius is 1 and the second radius is the square root of 5. By sketching that and then using the conversion equations and determining the bounds, we can evaluate this integral. So here we have a sketch of the graph. Notice you can slice it like a pie, and this is considered to be an R simple region. So the boundary, that shaded part here for R, is our smallest radius of 1 to the largest radius of the square root of 5. And then your bounds for theta would be from your smallest angle 0 to your largest angle of 2 pi. So you would determine your bounds of integration, make the substitutions for x and y into polar form, and also rewrite differential area as r times d theta. So again, if x equals r cosine theta and y equals r sine theta, and you make those substitutions, x squared would be r squared cosine squared theta, and y would be r sine theta. Okay, we make the substitutions for x and y. You make the substitutions for your differential area. Differential area is r times d theta. Your inside bounds are for r, your smallest to your largest radius, and then your outside bounds are for your angle theta, the smallest to the largest angle. Now you have a double integral. You would do the inside integral first by treating r as a variable and theta as a constant. You can take the antiderivative of r squared times a constant would be r cubed over 3. It's missing, it looks like it's missing a 3 there. And the antiderivative here would be r squared over sine theta. Okay, I apologize for that. There was no integration yet. This was simply multiplying the r in both terms. So now you can integrate r cubed to get r to the 4th over 4 and integrate r squared to get r cubed over 3. You evaluate r at square root of 5 and then evaluate r at 1 and simplify the result to get it to a single definite integral. When you get it to a single definite integral and simplify, you get this integral. You can use some advanced integration techniques, substitution, to evaluate the single integral. You can use the integration feature of a graphing calculator to evaluate this. If you use those advanced integration techniques and you can simplify, it looks like using the double angle formula. You can integrate this and then evaluate the lower and the upper bounds to get 6 pi.